Now we will have a closer look into fuel cells. We will have a look at what defines the performance and efficiency and what limits their durability. There are several types of fuel cells, which we can classify by means such as their electrolyte, operating temperature, or feedstock. Since we won't be able to cover everything, we will limit ourselves to low-temperature polymer electrolyte fuel cells, or LTPEFCs. Often, for the sake of simplicity, we will refer to them as PEFCs. As opposed to electrolysis cells, fuel cells are galvanic cells, and the reaction they are based on can occur spontaneously. This means that the higher the current, the lower the voltage. High resistances lead here to a steeper voltage decline and less usable energy, as you can see in the simplified graph. A curve such as this would indicate that there are only ohmic losses. However, losses in fuel cells are more complex. As you can see in the figure on the right, the shape is quite different than that of the figure before. Before we even draw current at 0 amps, we already diverge from the ideal. Losses due to gas crossover result in a lower open circuit voltage than the reversible cell voltage would theoretically be. As we increase the current in the low current region, the voltage declines steeply. This is due to the kinetic losses and strongly linked to the electrocatalyst we use. A poor catalyst will result in a more severe voltage drop in this region, whereas a good, highly active catalyst will result in a moderate drop. So far, we have, however, not found the ideal electrocatalyst for low-temperature PEFCs that shows no loss here. The initial activation region is followed by a linear region in which the drop of voltage is directly correlated to the current density. You should notice that this region looks like the simplified graph we have seen before. This dependency is following Ohm's law. The steepness here is defined by the ohmic resistances in the fuel cell. We normally assume that ohmic resistances and electric resistances, so the resistance towards conducting current, are identical. In the case of fuel cells, electric resistance is, however, only a contributing factor to the total of the ohmic resistances. Under usual circumstances, the ohmic resistance is defined by the electrolyte's resistance towards conducting ions, though, as this is the slower process. As you can see at the very right-hand side of the curve, the linear region is followed by a sharp decline at high current densities. This region is dominated by mass transfer limitation. Simply put, we consume our reactant too fast for them to be transported to the reactive zone, and thus we reach a more or less natural limit. However, we are also able to impact this region by the choice of materials that go into the fuel cell. More dense gas diffusion and catalyst layers can impact this region negatively and lead to the distinct sharp voltage decline already at lower current densities, which is of course undesirable. Although it is very important for us to understand these contributing factors, for the actual application of the fuel cell, the polarization curve itself is actually less relevant. When operating a fuel cell, the usual most important questions are: how much energy or power do I get out of my fuel cell? And depending on the application, I may also ask what volume this fuel cell takes up or what weight I need to take into account. And of course, how much hydrogen do I need to sustain the power output? Let's start with the power itself. It is quite easy to calculate for each point in the polarization curve, as it is simply the voltage multiplied by current, or current density if we're interested in the power density. It is important to note that the efficiency is defined by the operating voltage. The lower the voltage at which we operate, the lower the efficiency. This makes sense when we think about what we just discussed before. The further we move to the right of our polarization curve, the bigger the losses, and losses are nothing but energy we cannot use electrically. This is why we may not actually operate at the maximum power density, but rather find a balance between efficiency, power, and lifetime. More on that later. Another aspect to note is that drawing more current may not lead to a higher power output. If we take the point at 1 watt per centimeter square, for example, and we would want to get more power out of our fuel cell, we may achieve this by increasing the current at the sacrifice of efficiency. But once we surpass the maximum power, the output will actually go down again, and we may end up where we started, but at a far higher hydrogen consumption. The current is related to the amount of reactants that are converted, and at a lower overall efficiency. So as you have seen, even if the power output is the most interesting aspect for the application, we need to have a more fundamental understanding of the technology to be able to operate fuel cells efficiently. And we also need this understanding to operate fuel cells reliably. Improper operation can lead to detrimental conditions and result in early cell failure. These adverse conditions can occur within a blink of an eye, as you can see in the figure below. In particular, mechanisms related to charge transfer are very fast, but also issues occurring in relation to diffusion process are happening on a time scale that makes them difficult to detect. In particular, the latter can lead to what is called fuel starvation, which is a condition rapidly damaging fuel cell materials. Other factors, such as issues with water or temperature management, can be just as critical, but are slower and thus give the opportunity to monitor and interfere. But also, if we make no mistake in how we operate our fuel cell, it won't last forever, as materials undergo degradation, or put simply, they age. Now, let's have a more detailed look into how materials age and what is accelerating these mechanisms. In the end, every component that goes into a fuel cell, or more holistically, a fuel cell system, can age and can potentially be the lifetime limiting factor. This includes seals, pipings, etc. But here and now, we will focus on the electrochemically functional components. In the electrolyte layer, we have an electrocatalyst that can be deactivated or physically lost, and we have carbon-based layers which can corrode or lose the porosity. These processes are accelerated by elevated temperatures, humidity, potentials, and gas crossover. Gas starvation also shows similar results. We also have a polymer electrolyte membrane. This thin layer separating hydrogen and oxygen can tear due to mechanical stress or degrade chemically, which can lead to the emission of fluorinated species. These processes are impacted by varying or low humidity, open circuit voltage, and gas crossover. To conclude, fuel cells are galvanic cells, and their performance and efficiency are defined by how we operate and what materials we choose. And even when the power output is the most relevant for the application, it is important for us to understand what losses originate from where. This is especially important when we want to maximize durability. Harmful conditions can rapidly do damage, but even if we can avoid them, the operating parameters we choose will impact which aging process is dominant. This is a balance we carefully need to make.